All right, so before we jump into this, some reminders on the board. I did decide to move the quiz to Friday. It will cover solutions. So that's going to be finding what the molarity of the solution is or finding moles from the solution, dilutions, balancing equations, which we're looking at, and also transcribing them. The three acids I told you about, they're written on the board over there, and double displacement reactions, which we're going to talk about today. So several different topics that are going to be on there. I don't want to push it any farther and have to include more. Don't forget you have an active chemistry assignment that is due tomorrow night. Any questions? Okay, so with this, when we change this into a chemical equation, we have to remember our rules for the nomenclature, the names of ionic compounds, the names of covalent compounds. So we have an ionic compound here. We have an element, an ionic compound. So what symbol are we going to start off with for sodium? Na. And then Na has what charge? +1, right? And the reason this is important is we need to know how many sodiums to put with the anion. So we're going to check to make sure we have the right numbers. All right, so this is going to be a +1. What's bromide's charge? So that's in the second to last column. The very last column would be 0. So the second to last is -1. All right. So how many bromides do I need to match up with sodium? Just one, right? They balance each other. So that works out nicely. Now, this also says solid. So I want to include that as a phase in the equation. Reacts with just means put a plus. And then chlorine gas. So since it just says chlorine, that means it's an element. And we have to think about for chlorine, is this sufficient? Why not? This is one of 7 special elements that do what as a natural or as an element. This is one of our diatomics. So remember on the periodic tables in here, the dark green, those are our diatomics. Nitrogen through fluorine, fluorine down through iodine. So all of the halogens are diatomics. So when chlorine is a pure element, unless it just says atomic chlorine, so this is just elemental, not atomic, you need a 2. All right, to produce or yield is going to be an arrow. Do I need to change any numbers on NaCl? No, because it's still +1 for sodium and chlorine right above bromine is going to be a -1, so they balance out. It does say solid, so I'm going to include the solid here. And then what about bromine? How do I write that as an element? Br2, because it's in that same column with chlorine where all of the halogens are diatomics. Bromine is one of 2 liquids that are found on the periodic table at room temperature. Anybody know the other one? It's a metal, a liquid metal. Mercury, yeah. They used to call it quicksilver. It's not really silver. Silver is a completely different element, but it was silver in color and it could move. So it was quick.
So you don't have to care, there's 2 chlorines on the left and on the one on the right.
We are going to care about that because now that we have the equation written, we want to balance it. Okay, so balancing. Now on your quiz, what I will do is I will have a little line in front of each of these things. If you don't write anything, I'm going to assume you skip the question and it's just wrong. But if you write any numbers, then the blank spots I will assume that are that invisible one. All right, so you said there's 2 chlorines here. So we're going to have to put a 2 here to balance that out, right? And then what do we need to do? You got two sodiums.
Maybe two.
Yeah, so there's gonna be a sodium over here or two over here as well. Now, does that balance everything for us? Yeah, that looks fine. Okay, and we can double check. Two sodiums, two bromines, because 2 times 1 is two bromines, two chlorines, and 2 times 1 is two chlorines. That one's balanced. I'm going to be talking about reaction types later. This type is called a single displacement because this single element is displacing one of the elements in the column. We're not going to worry about single displacement just yet. We'll get to those later in the week. All right. Let's do this one next. And we don't have to keep moving the computer back and forth. This one's kind of hard. All right. So you're going to run into an even odd conflict here. If you can figure out how that works. All right. Anybody feel like they've got this one? What do you think? If you think you've got it, what do you think this number is here? That's a 2. Anybody get a different number here? What'd you get? 4. Okay, so it is one of those. All right. So, anybody feel like they're stuck? Okay, handful of people. So I would go here and say, okay, here's an iron, and I'm going to save oxygen for last, both because it's a pure element and because it appears twice here. But there's 2 irons over there, and I want 2 to be here, so I'm going to put 2 here. And then that means I have 2 sulfurs. So I want there to be 2 sulfurs on the other side. So I'm going to put a 2 here. All right. Now, is this where people started getting stuck? Okay. So this is the even odd conflict because this has to be an even number of oxygens. But if we count up our oxygens over there, we've got 3 from the Fe2O3, and then we've got 2 times 2. So 4 plus 3 is 7. We have an odd number over there. That makes it hard to keep moving on. So what do we do when we have an even odd conflict? Double it. Yes, we're going to double everything that we've looked at already. So we haven't really done this one. We're going to ignore that for right now. So this is going to be a 4. This is going to be a 2. And this is going to be a 4. Okay, so we're doubling everything we've done so far. And that means I'm going to go back and change these numbers. Okay, so iron, there's now 4. Sulfur, there's now 4. Over here, 2 times 2 gives me 4 sulfur, or 4 irons, and 2 times 3 is going to give me 6 oxygens. My sulfur is a 4 here, and my oxygen is 4 times 2. So 2 times 3 is 6. 4 times 2 is 8. So 6 plus 8 is 14. All right, so our iron is balanced, our sulfur is balanced. We have 14 oxygens on this side. So what number is going to go here? 7. So usually if I give you something like this on a quiz or a test, I attach a bonus point to it. So if you can get that one, you get extra points on the quiz or test. So we have iron nitrate, but when we say the name of it, we usually put a Roman numeral for iron. So here our nitrate is -1. That's just, nitrate is always -1, but there are 3 of them. So the 3 on the outside means there's 3 of that whole grouping. So if I have 3 -1s, what is the charge of the iron atom? +3. Now for balancing, we don't really need to know the charges, but we're going to do something else with it in just a minute. So we're going to need that. And then over here we have potassium oxalate. Oxalate is one of the ions on your polyatomic ion sheet that I haven't had you memorize yet, but it has a -2 charge. I'm gonna suggest with this that you keep the nitrate all together. Consider that as one thing. Don't split it up into the nitrogen and the oxygen, because you've also got oxygens here. So if you try and do all those oxygens, it's just gonna be oxygens all over the place. So I'd say just call this A. I have 3A over here. Right now I only have 1A, and try to balance that. Similarly, you could call this B. I have 1B over here, and over here I have 3B. Keep it one thing together as you try to balance it. All right, so I'd start with this iron here, and I'd say I've got 2 irons here and only 1 here, just like on the last one. So I'm gonna put a 2 here. So how many nitrates does that give me? 6, because I've got a 3 on the outside and a 2 over here. On the inside, that just refers to the oxygen. So it's just saying this group of things has 3 oxygens, but that group of things is going to stay together. So I have 3 of this thing I'm calling A. A is the nitrate. 3 times 2 is giving me 6. Then I'm going to go over to this side. So my iron's okay here. I've got, keep changing iron to fluorine. I've got 2 on this side. And then over here, I need 6 of those nitrates. So what am I going to do? What do I put in front of the K and O3? A 6. Yeah. So I've got 6 of the K plus, and I have 6 of the NO3 minuses. All right, so now I want to go back to this side because my potassium isn't quite balanced yet. So I need to get this balanced, and I have gotten erased a 2 here. So what needs to go in front of this chemical to balance? A 3. So coefficient times subscript. So we're good there. And then fingers crossed, hopefully that oxalate works itself out. So the C2O4 2 minus, that's what I'm calling oxalate, has a coefficient of 3. And then this didn't have parentheses before. I was trying to show you the grouping. There's really just one. Okay. So times 1 gives me 3. Over here, I have a 1 as a coefficient. And a 3 outside the parentheses. So I have 3. Okay. So when you have like ionic compounds all over the place, try to keep the polyatomic ions together. Now there is one occasion in lab coming up where you can't do that, and I'll give you a warning on that when it comes to that. But as a general rule, it's helpful if you do that. Yes.
Are you gonna list the charges on?
So typically we don't put the charges when they're in a compound, but I'm going to do something with this in just a minute where we're going to need to know those charges. So we're going to come back to that. Okay, but first let's look over at our hydrochloric acid and see if we figured that one out. All right, so our 3 strong acids over there, the very first one is hydrochloric acid. When you see the word acid, assume that it is aqueous. Because if it is a gas, which is the alternative, then the hydrogen can't separate out. Okay, it has to be dissolved in water for the hydrogen to separate out. So we would start with HCl 8. So I'm gonna give you a second to try and work on that one. All right, barium is in group 2, so it's Ba. What's the formula for hydroxide? OH, and what's the charge on hydroxide? This one's a -1, and barium being in group 2 is a +2. So how many hydroxides are we going to need? 2 of them, okay? We can't just do this. That's really just another way of writing water. you have to put parentheses around it, so the 2 applies to everything. 2 oxygens and 2 hydrogens. All right, it tells us that that is also aqueous, so I'm gonna put an AQ. And then it says it produces, so that produces means I get an arrow. Okay, so this says chloride. Do I add the oxygens in there? We have some of our polyatomic ions that have oxygens. Does "ide" mean there's oxygens? No. "Ate" or "ite" would mean oxygens. "Ide" just means chlorine's the only thing there. What's the charge on a chloride? Then group 17, right next to the noble gases, which are 0. So it's -1. So just like with this one, we're going to need 2 of them. Barium is always going to be +2, unless it's like neutral by itself element kind of thing. And then finally, water. Oh, you recall that aqueous. Water. Okay, so here's a situation where we have hydrogen appearing in a couple of different places, but we don't have hydrogen as a pure element to balance it out. So this one's going to be a little bit trickier to balance. I'll give you a second to try it. Right, I'm saving hydrogen for later because it's appearing all over the place. For my chlorine, I'm going to put a 2 in front here. So then now I have 2 chlorines and 2 chlorines. Everybody get that okay? All right. Barium is already balanced. I got 1 and 1. So now I got to deal with my other elements. Right now I have 2 oxygens. So since it is inside the parentheses and there's a 2 on the outside of the parentheses, I multiply the 2 from the outside by the invisible 1 here and the invisible 1 here. That's how I have 2 oxygens. So then going over here, what do I need to do to get 2 oxygens? The 2. So what does that do to my hydrogens? How many do I have? 4. All right. So let's see how many I have to see if I need to adjust it. How many hydrogens do I have coming from HCl? 2. And how many do I have coming from the OH? 2. So I have a total of 2. Okay. So in an ideal world, that last element works itself out, which is why we save the ones that are appearing in multiple places for last, because hopefully we don't have to think about them too hard if everything works out. Okay, so these last 2 that we've looked at are what are called double displacement reactions. And they are also ionic reactions. Now, we talked on Friday about how we can write ionic reactions, so we're going to look at this one first. So as they are written, we call these the molecular equations. Remember, I hate that term because aside from water, those aren't really molecules, they're ions. When they're aqueous, the ions separate from one another, okay? We can also write the total ionic to really show that in water, all of the ions are separate. So when we do that, the coefficient gets applied separately to each ion. Okay, so I'm going to have a 2 in front of an H and a 2 in front of the Cl. I also want to show the charge for each compound. And whenever there's parentheses, the parentheses go away and the 2, the outside number, is going to become a coefficient. So we'll talk about that in just a second. Let's start over here. So we're going to have 2H. What's the charge on that H going to be? +1. So first of all, it's in that first column, but also it's combined with the chloride, which is a -1. And then whatever the phase is here, which should be aqueous, is going to apply to both ions. I have only 1 Da, but its charge. All right, now this formula says that every time I have 1 barium, I have 2 hydroxides. And those hydroxides individually are units, but when they get dissolved, 1 hydroxide doesn't have to stay near the other hydroxide. So that's why we get rid of the parentheses. So right here, we're writing it as if they're all riding in the family car. Both hydroxides are in the back seat, fighting over who's not taking up too much room and that kind of thing. Then they're going to arrive at the amusement park of the water. And if that's this water park, the two hydroxides are going to go in different directions. Okay, so we're going to show that they can go independently by making that 2 a coefficient. Okay, then we have this side, barium 2 plus aqueous plus 2 chlorines. Again, this isn't going to be Cl2 the gas because this is aqueous and these are ions. As part of this compound, these are Cl minuses. So I'm going to put Cl minus and the subscript is going to become the coefficient. Okay, so that tells me I have 2 of those. And then I have 2 waters. And I hope we all know water is a liquid. Okay, that's my total ionic equation. That's a lot to write. That's a lot to look at. There's really only one chemical reaction going on. Yes. Because it doesn't have aqueous next to it. So we're only going to split up the things that say aqueous. If it has a liquid or a solid, we're going to assume it stays together as a compound. And that's going to be real important for this next part. So when we want to write just the interesting part, we're going to leave out the ions that aren't doing anything. So some of these ions are like the fans at a game. What do we call those guys that are at the game that are watching but not doing anything? Spectators, right? So how do we know they're spectators? We're going to look for something with a charge, because it's ionic, that has an AQ next to it. That tells us it's still dissolved. And it appears exactly the same on both sides. So the charge didn't change, the number didn't change. It's this, there's 2 H pluses on one side, there better be 2 H pluses on the other. If there's not, it's not a spectator. So when I look, there are no H pluses on my side. So that's not a spectator. When I look at the chlorides, though, I have 2 Cl minus here and 2 Cl minus here. So that tells me that's a spectator. So I'm going to draw a line through those. Because remember, they're not playing the game. They're just watching in the stands. And if that's a negative species, I should have a positive one that is also a spectator. There should be at least one of each. So what's my positive spectator? Barium. Cross that out. So that's what we call the total ionic. But the one we're interested in is the net ion. All right, so this is with no spectators, as if this is a closed practice. Nobody's allowed in but the players. So we're going to look at the things we haven't crossed off yet and write those. 2H plus aqueous. This we crossed off, so I'm going to skip it. This we crossed off, but the 2 OH minuses we haven't. I'm going to write that down. My arrow. I crossed off the barium, I've crossed off the chlorides, and then I'm going to write the water. So the fact that this wasn't aqueous here tells me that it was part of a reaction. That's why I didn't split it up. Okay. So overall, my reaction, and we're going to call this a neutralization reaction. I'll get to how we identify those in a minute, but our neutralization reaction has 2 hydrogen pluses and 2 OH minuses, forming 2 waters.